being promoted by all the companies. So let's talk about how the heat is transferred in the radiant section. I keep on going to basics, and I will find that the more you understand basics, the better you will appreciate your furnaces. So if you see over here, there are two radiation mechanisms by which the tubes are being heated. One is the direct radiation, and even in direct radiation, there are two. One is the flame radiation, and the second is the flue gas radiation, which basically takes place because of carbon dioxide and water vapors. Those are the molecules which are actually radiating. So those are the two this thing. So the direct radiation, flame and CO2, this thing. And then we have re-radiation. So basically the radiation goes back to the refractory and hits back the back of the tube. So that's basically what is happening. And the next one is convective. As I said, anywhere between 10 to 12% of the heat transfer takes place by convection means. So that's what is happening because the molecule movement of the molecules. Convective heat transfer is associated with movement of flue gases. And once this tube has absorbed radiation and convection heat transfer, now the challenge is conducting that heat from the outside of the tube to the inside of the tube. And that's where I think there are two challenges. We are talking of scaling on the outside, and especially high temperature tubes can scale pretty fast. And the second one is coke on the inside. As you all know that the cracking, no matter how good a cracking you have, you will always get coke formation. So that's another impediment to heat transfer. And once the heat is transferred inside, then by convection, the fluid receives the heat and it gets heated and then the reaction starts. So that's basically how the heat is being transferred by in the radiant section. So I'm just trying to show you what I talked to you about this thing. This is generally the refinery heaters, and this is the cracking heaters. We have burners on both the sides. So we have uniform heating, but it does require double the number of burners as compared to this configuration. So that's basically the double fired arrangement we have. So modern ethylene cracking furnaces are basic. You can either have a twin cell heater, like two radiant sections with a common convection section and ID fan on the top, or you could have two furnaces which are like mirror images, and they are put together. And the reason they are put together is it offers the designers a lot of structural stability. They are able to put a common structure and then it becomes a lot more stable. That's basically the furnaces are attached. So they are built in pairs, maybe 2, 4, 6, 8. That's typically how, you build the furnace. A lot of furnaces has even SCR systems. They are meant for reducing NOx, selective catalytic reduction system. So they are built into the convection section and they reduce the NOx emissions in the furnace. All right, we have, I think, so maximum ethylene production requires what? Well, This says all the four answers are correct. You need a highly saturated feedstock. That is the first requirement. Then you need low hydrocarbon partial pressure at the outlet. As you see, when you crack ethane and make ethylene plus hydrogen, the volume is going up. And when the volume goes up, it means if you want the reaction to proceed at the fast pace or reaction to complete, you need a low hydrocarbon partial pressure. Very simple, you know. So you need low hydrocarbon partial pressure. Uh, High coil outlet temperature, the higher you go, the more ethylene or the product you make. And then again, the short residence time is basically the shorter time you have, the more desirable products you will generate. You know, if you let it give a higher residence time, you will have cracking, but you will have other products also coming out. So all the four uh, uh, parameters are correct here. So generally, that once you know what capacity furnace you are going to be building, uh, you find out the firebox dimensions, how many radiant coils, how many fireboxes you will have. You could be going with the short versus long residence times, although most of the coils are short residence time these days. A high temperature and low partial pressure. So the way they design the coil, you know, is making all the difference over here. But other than that, the box and the convection section remains more or less the same. There is not much difference. In fact, you people have been retrofitting different coils to get more capacity from the cracking furnaces. So the coil surface area requirement and residence time requirement is selected by the diameter of the coil, and the flux decides how much surface area we need. So it's basically the coil kind of is designed based on these three parameters. Uh, Generally, you will see we have, as I said, two radiant sections combined in a mirror image, vertical radiant coils. Most of the radiant sections will have a height of 15 meters or 50 feet. Width is anywhere between 6 to 10 feet. We have burners on the side or on the floor, and they all operate on slight negative pressure. That's typically what we kind of envisage in our designs. So you want to find out what is the outlet temperature you maintain in your cracking furnace. If you have an old cracking furnace, the temperature is going to be lower. If you have a new cracking furnace, the temperature is going to be much higher, you know. So most of this thing is, I think that's where most of the cracking furnaces operate, around 1450 to 1550. Thank you for your participation. This is a very nice graph drawn by our team, and it shows the coil lengths. Typical coil lengths are anywhere between 100 to 130, 40 feet. That's typically the coil length. And it shows the coil temperatures, the fluid temperatures, you know, process gas temperatures. This is for the naphtha, and the yellow is for ethane, which is another very common feedstock. And we are talking of going all the way up to 840 degree centigrade, which is about 1500 plus 50, or you know, even higher. As I said, maximum allowable flux typically around 27,000 BTU per hour plus foot square or 85 kilowatt per meter square. Coils are in the center. That's typically how these things are designed. This is a typical design of a cracking heater. Duty is about 75 million kilocalories, 300 million BTUs. Total process duty is around 240. Waste heat recovery is around 62. Radiant section heat duty is around 130. So you can see about 42, 43% is the radiant duty in the radiant section, and rest is in the convection section. So convection section is bigger actually, it's 170 million BTUs, radiant is 130. Firing rate about 315, and the efficiency you can see is almost like 94, 95%, So very, very good efficiency is typical in cracking heaters. This is giving a typical parameters. Inlet temperature in the radiant section is around 1050. Flux about 31,000. Maximum flux is 37,000. The ratio between the two is about 1.2. Maximum tube metal temperature is around 1950. Bridge wall temperature, and you can see the bridge wall temperature is the temperature of the flue gas leaving the radiant section, and this is very close, 2150. Volumetric heat release around 8,000. Actually, this looks a lot lower nowadays. They even go to 20,000. Excess air around 12%. So these are the typical parameters of a radiant section for an ethylene cracker. You can see this furnace that has a height of 40 feet, width about 12 feet, length around 30 feet. It has 6 coils per pass, and there are basically 12 burners, So looks like a little smaller heater, but that's typically how the radiant section will be configured, So very briefly, we want to talk to you about a different type of coils. We have 3 types we have kind of shown over here: single pass, U-Coil, and a hybrid coil. If you are going for short residence time, then you use tubes of small diameters. If you want to have a medium residence time or high capacity, you use larger tubes. That's basically what. So this is a single pass coil. There is there's only one, this thing which comes here, and floor firing is at the bottom. And this produces highest olefin conversion. This is very similar to what Kellogg had their millisecond furnaces. That's basically the concept over here. Is the flow is from bottom to top, and that's a single pass. It has the shortest residence time. And the next one is a very convenient one, or a typical one, which is basically a U-Coil, and that can have 2 passes over here, as we are saying, or maybe 4 passes or 6 passes, and that's basically the design of the coil over here. You will see the box remains the same. The box is not changing, And these are the more current coils. These are the hybrid coils. As you see, we have the smaller tubes and like 6 smaller tubes, and then joining in one larger tube and going towards the outlet. By having a larger tube, we are able to control the outlet pressure, keep the outlet pressure low, so we get a better this thing. And here we can get the maximum heating taking place. So this is how, and you can see over here. So that's a typical coil design, These are some of the licensors. You must be very familiar with them. ABB Lummus. Actually, it's not ABB Lummus anymore. But they have this short residence time SRT furnaces for last 50 years. Kellogg developed millisecond furnaces. I think they have licensed it to Exxon now and UOP also. And then Technip bought KTI, and then later they bought Stone and Webster. So they have two types of designs, HSC and USC. That's basically the two types. And then Linde has pyrocrack and Linde Celas combined. So you only have a choice of about 5 licensors, and they cover the whole ethylene industry in the world. This is a design of a SRT5 and SRT6, and you can see over here, the same concept, smaller tubes, and then we have the larger tubes towards the outlet. That's basically the SRT coil. We are able to have a residence time anywhere between 0.15 to 0.2 seconds. Similarly, we have a Linde pyrocrack, and here also we have this multiple coils coming and then combining into this thing. Here we have 4, 2, 1. This is 2, 2, and this is 1, 1. So these are different coil configurations to limit the residence time in your furnace and get the required yield of ethylene. So when we talk about radiant heat flux, these are the typical numbers. For ethane, we use 23 to 27. Propane also same. Naphtha, we can go up to 30,000, or gas oil cracking even higher, so 26 to 32,000. All right, let's have a quiz, So so you will see, actually none of the answers is wrong, I mean, depending on if you had an old furnace, your crossover temperature may be lower. If you have a new furnace, your crossover temperature is going to be higher. So I apologize. I think this should have been more like a poll instead of a single correct answer. But what we want to show you is, in the last 25 years, they have been trying to preheat the feed in the convection section to a very high temperature. And that basically reduces the heat requirement and also reduces the residence time in the radiant section. If the feed is already heated to 1250, I just need to heat it up to about 1500 or 1550, so then I don't have to do too much heating, sensible heating. Well, thank you for participating. So you can see over here. Okay, just give me a break. Oh, yeah. We have a energy conservation in our offices. So if you don't move, the light goes off, So as I said, crossover temperature, we're talking of ethane cracking, propane cracking, naphtha is much lower, gas oil is even lower, heavy oil is even lower. So you can see how it is increasing as the feed becomes lighter, limited by the feed. And the reason is because if you heat it even further, then it will start coking, So okay, as we talked about that the furnace is going to be coking, So what is the typical temperature rise in your furnaces, these numbers are again, this was again a poll, I think we should have fixed it. But anyway, this is 1 to 5 degrees, the best furnace if you have 1 to 5 degrees. If you have 4 to 10 degrees, then you are having, or 8 to this thing, you will have a much faster coking, So these are the typical temperature rise. If you have a cracking furnace, you will be increasing the temperature 1 to 2. If you have as the feed becomes heavier, the coking rate keeps on going up. So you can see typically up to about 8 degrees heavy oil, So that basically determines the run length of your furnace. I mean, if you have got 1 to 2 degrees, then maybe you can run all the way up to 100 days or even 120 days. But if you have 3 to 5, you can run only 45, 50 days. So that's basically how your run length will be taken care. So one thing I want to introduce, and what we have been doing is, most of the time when we talk of coking, we are only talking of coking from the coil side. But we all know that it is the flue gas side which also contributes to coking. And what we have been finding is that these are the 4 important parameters which can help you reduce the coking, or if not taken care properly, will accelerate the coking. And the 4 parameters we want to talk about start with the burner heat release per burner, how big your burner is, then the clearance between the burner to tube, and the burner to burner spacing, how your burners are spaced, and then the burner air side pressure drop. And we'll talk about these. We think these are the 4 parameters. If you focus on these, you will be able to reduce the coking in your cracking furnaces. So let's start with the first one, heat release per burner. All we want to tell you is that if you use a larger burner, you will have more coking. If you use smaller burners, you will have less coking. That's basically this thing. Yeah. And you can see over here, I mean, if you have shorter flames, we will have more uniform. I mean, the whole concept is based on uniform heat transfer. The next is burner to tube clearance. This is very, very critical. We have found that flames, when we do CFD modeling, flames tend to lean towards the radiant tubes because they are at a lower temperature. So flames are looking for low temperature, so they tend to lean. And the greater the distance, more uniform heating will take place. What has happened in the industry is, in the last 20-25 years, we have started resorting to low NOx burners, and low NOx burners, as you know, have a very long flame length, almost 2 to 2.5 times the flame length, and that increases the chances of flame impingement. So if you can keep your flames away from the tubes, that will be the best. And as I said in the beginning, since it's such a high temperature furnace that once it starts running, you cannot see any flame because the bridge wall temperature or the firebox temperature is more than 2000 degrees F. So it's virtually impossible to see the flame. So you can only, see it during startup or when it is running cold. Another important parameter we found is the burner to burner spacing. We think the more burners you have, the better uniform heat transfer distribution you will have, because more burners means shorter flame lengths and uniform heat transfer across the whole length of the heater. So see if you can think of, I mean, if there is a possibility of installing more burners in your furnace, that will definitely help in improving the flame patterns. All these things are based on the flame patterns, and these are all practical things. So burner air side pressure drop, that's another, if you look at the burner and if you look at the flame, we are using two sources of energy for mixing and generating a flame. We have fuel gas pressure, and then we have the combustion air or the draft loss. Fuel gas pressure, typically we use 25 psi, and air pressure is very, very important, and especially because the volume of air is anywhere between 15 to 20 times the volume of the fuel gas. So the higher the draft class, the tighter will be the flame. If you use forced draft burners where we have 2 inches or 3 inches of air pressure, then you will have even tighter flames and you will have much better combustion. So these are the 4 parameters I talked about. Nobody talks about coking. In fact, the burners don't never figure in radiant heat transfer calculations. That's the situation, that there is no parameters. And you will see, I think I will cover it, that all heaters are still designed based on 1940s Lobo-Evans correlations, So the number of burners or these things do not come into the picture, So I just want to give you a little brief about our inclined firing technology. Our inclined firing technology is very simple. It is based on diverting the flames away from the tubes. And our CFD group did this modeling of a small cracking furnace. And what we have seen is, if you do it, we are able to lower the temperature by 50 degrees to 100 degrees in cracking heaters, and you can see the CFD model over here. There are 2 rows of burners with a tube in the center, So this is typical configuration of a conventional vertical cylindrical firing, vertical firing of front firing. And here what we had done is we have put the burners at an angle of about 7 degrees, and we are trying to fire it across the wall, around the wall, And I just want to show you a few of these things. So you can see the difference, You see the flow gas temperature contours are closing towards the tube, Whereas when I do the inclined firing, those red zones kind of get disappeared. Now this is looking at the flame length. You can see the flames are so close to the tubes over here, and here they are very much away. The flame length does go up, but it does give you a much better uniform heat transfer. You see, the beauty of the radiant section is the radiant section does not need a medium. If you are looking at radiation, we are able to receive heat from the sun even though it is millions of miles away from us, So it does not need a medium. Similarly, you don't need to keep the flames closer to the tubes. The flames can be as far away from the tubes and you will still receive the heat transfer. In fact, you will receive the better heat. The farther the flames are, the better heat transfer you will have, So that's the basic concept, Keep the flames away from the tube. Very simple concept. It can be done using your existing burners that you don't even have to change the burners,